Hello, everyone. I'm Shih-Wei from Columbia University. Today, I'm going to present our work about verifying a commodity multiprocessor KVM hypervisor. Computation is shifting to the cloud. Cloud computing is supported by a technology called virtualization, which enables multiple virtual machines to run on a single piece of hardware. Virtualization relies on a privileged software called hypervisor to manage the virtual machines and their resources. To satisfy the requirement of cloud computing workloads for performance and functionality, hypervisors are becoming increasingly complicated. Many commodity hypervisors include a full operating system kernel to reuse its existing functionality. The increasing complexity in hypervisors also results in more bugs. Attackers that exploit vulnerabilities in the hypervisor codebase can gain full access to all hosted VM's data, potentially compromising the VM user's confidentiality and integrity. Formal verification offers a solution to improve hypervisor security by proving that a hypervisor is implemented correctly and contains no vulnerabilities. In general, formal verification involves three components. First, the implementation of the program. Second, the specification that specifies the behaviors of the program. And third, the hardware model that defines the machine interface. Verification involves proving the implementation running on the hardware model satisfies the specification. The soundness of the proof relies on the accuracy of the hardware model. Previous systems such as SEL4 and Certicos were verified using overly simplistic hardware models without features such as TLBs. Their proofs may not hold on real multiprocessor server hardware. More complex models do exist, but they have not been shown to be feasible to verify real software. To address this problem, we introduced a new approach to verify real software on real hardware. We introduce a layered hardware model that captures realistic hardware features, yet is simple enough to be used to verify commodity software. Layering tailors the hardware model to the software needs. Software layers that use low-level hardware features are verified using a more detailed hardware model that includes all the various hardware features, such as Model A. Software layers that do not rely on low-level hardware features can be verified using a simplified abstract hardware model, such as Model B. So long as we can prove that the software using the simplified model is equivalent to the software using the detailed low-level model. We use the layered hardware model to verify a commodity multiprocessor hypervisor. We built on our previous work, SeKVM, that verified a multiprocessor KVM hypervisor to ensure that SeKVM's proofs hold on the multiprocessor server hardware used in the cloud. To verify a KVM, SeKVM leverages ARM virtualization extensions and retrofits KVM into a small K-core and a large set of hypervisor services, Kserv, such that we can verify the entire KVM hypervisor by reasoning about just K-core. We structure K-core's implementation as a hierarchy of layered modules that build upon the hardware and each other. We construct K-core and the layered model to match each respective layer to an appropriately abstract machine model. We describe how we use the layered hardware model to verify SeKVM's TLB management. TLB caches page table translations to improve paging performance. ARM's TLB is tagged, so the software does not need to flush the TLB when switching CPU execution. However, the software needs to flush the TLB when page tables are updated. Correct TLB management is crucial as a bug can break isolation among VMs. For example, consider the scenario in which the TLB caches mapping from a guest physical page GFN1 to a physical page PFN1. Suppose K-core unmaps PFN1 from VMA and maps it to VMB. It needs to make sure to flush the TLB properly after the unmap, but if it instead flushes the TLB before the unmap, a problem can occur. A multiprocessor VM like VMA uses the same stage 2 page table on multiple CPUs. VMA running on CPU 1 accesses PFN1 after the TLB flush at time t1. The access results in the hardware refilling the entry for PFN1 from the page table to TLB. VMA can access PFN1 through the TLB even after K-core unmaps the PFN from VMA's page table and maps it to VMB. This breaks VM isolation. To protect VM security, K-core must flush the TLB after updating page tables. Our layered hardware model captures tagged TLB behaviors and operations, so we can verify the K-core layer that manages TLBs does so correctly. Since the TLB is just a cache of page table mappings, if it is correctly managed, we can refine the complex model with the TLBs and page tables of the lower layers to a simpler model that only includes the page tables at higher layers. This would reduce the proof burden because we can then use the simpler model that hides the TLB to verify the higher layers of K-core that do not manage the TLBs. The intuition of our TLB proof is that if the TLB is not managed properly, the pages that can be observed through the TLB will be a superset of the pages observed through the page table. As demonstrated in the buggy example we showed earlier, the resulting TLB can either contain an earlier and the current version of the page tables. The TLB may include stale page table entries if the page table is updated, but the respective TLB entry is not flushed by the hypervisor. We proved that the K-core layer that can update page tables guarantee that the pages observable through the TLB are the same as those in the page table. To model such observations, we introduce a concept of page observers to represent the set of all possible principals, either VMs or K-serve, that can observe a physical page, PFN, through TLBs or page tables. We merge consecutive page observers that are the same into page observer groups. In the example here, VMA can observe PFN1 through the TLB and page table, so the respective page observers and the observer groups for PFN1 include VMA. Consider K-core executes the three follow-up steps shown on the left. First, K-core unmaps PFN1 from VMA's page table. The page observers for PFN1 via page tables become null as a result of the page table unmap. The page observer groups for page table include the new null observer. VMA can still observe the PFN through the TLB after the unmap, so its page observers remain the same. Next, K-core flushes the TLB for the entry that maps to PFN1. The resulting page observers through TLB become null after the TLB flush, and the TLB's page observer groups include the new page observer. Finally, K-core maps PFN1 to VMB's page table. Intuitively, the resulting page observers from PFN1 through page table contain VMB so as the ones via TLB. The latter is because the translation to PFN1 using VMB's updated page table can be cached in the TLB. The resulting page observer groups for TLB and page table both include the new page observer view. To prove that TLBs are maintained correctly by K-core, we show that starting with the same page observer groups of TLBs and page tables, the resulting page observer groups produced by the executions are still the same. Based on this approach, we verify that the example execution manages the TLBs correctly. We can also use this approach to detect incorrect management of TLBs. Consider the buggy example that we discussed earlier. Since TLB was not flushed after the unmap, both VMA and B can observe PFN1 using the TLB, so they are thus included in the page observers for the PFN through TLB. The resulting page observer groups for TLB are different from the ones for page table. This allows us to detect the bug. We take the detailed model that accounts for TLB and multi-level page tables and verify that K-core's lower layer software with the model refines K-core's higher layer software with a simpler abstract model that accounts for a flat map, so that the higher layer software can rely on the simpler abstract model. We take a similar approach in modeling other hardware features to capture realistic hardware behaviors. Details are presented in the paper. For example, while the detailed hardware model captures multi-level page tables, the simpler abstract model can treat the page table as a simple single level map. Similarly, multi-level caches can be treated as a single unified cache. We use COC to implement the layer hardware model and verify SeKVM. We prove the functional correctness of K-core's implementation, which includes 3.8 K lines of C and assembly code. We prove that K-core's entire implementation, modularized into 34 layers, refines its specification. In addition, we use the layered hardware model to verify that SeKVM protects VM confidentiality and integrity, ensuring that the verified security properties hold on multiprocessor server hardware. We tested some of the commonly used server application workloads on ARM server class hardware running SeKVM. We run workloads on a VM using baseline KVM and SeKVM. The results in the graph are normalized to bare metal execution, so lower numbers mean better performance. The results show modest overhead on SeKVM compared to unmodified KVM. In addition, we compared the performance of SeKVM versus SeKVM that flushes all entries from the TLB and switches between the VM and hypervisor to measure the performance impact of a verified implementation that models a tagged TLB versus the one that models a simplified TLB without tagging. As shown in the graph, frequently flushing TLBs incurs significant overhead to VM performance. In conclusion, we introduced a novel layered hardware model that is simple enough to be used for verifying real software while accounting for realistic multiprocessor features. We use the layered model to verify SeKVM, a multiprocessor KVM implementation, ensuring that the verified guarantees hold on multiprocessor server hardware. The verified SeKVM implementation can thus take advantage of the widely used multiprocessor features to retain KVM's overall feature set and performance. That'll be all for my presentation. Thanks for listening. I'm now happy to answer questions.